Rational Computing. Introduction. Square Roots. In this series of videos, we'll explore solving traditional, irrational problems with integers and integer ratios. In the modern world, we have calculator apps, computers, and code libraries that protect us from the details of math. Perhaps rightly so. Abstraction is very powerful. It allows us to focus on bigger and better things. Abstraction in some cases can also be synonymous with obfuscation. Losing track of the fundamentals can stall or inhibit innovation. In this series, I'll be reviewing some of these fundamentals in a way that I hope is clear and intuitive. We'll get started by looking at square roots. Objective. Calculate any square root to any degree of precision desired, using only integer ratios. What is the simplest way of doing this? First off, let me introduce the concept of an additive sequence, where new values are generated by adding existing ones together. In this case, we are starting with the values 0 and 1. We construct the next value by adding them together. We continue by adding the newest value and the one before it. As a side note, by looking at this abstractly, we can see that all additive sequences with two terms embed the Fibonacci sequence. I was watching a math video when the professor made a statement that, well, it didn't make sense to me. He gave the definition for the Fibonacci sequence. My problem is, I happen to know that the square root of 5 doesn't come from nowhere. I also know how to generate it from an integer ratio. And it uses the Fibonacci sequence. Now, I'm not being closed-minded about this. There very well may be a good answer. But the question came to mind. Can we actually know root 5 without computing the Fibonacci sequence? Even if just accidentally? I'll leave this as an open question. However, I suspect that definition might be too strong of a term in this case. Take that with a grain of salt. I'm just a programmer and not a mathematician. To a programmer, the square root of 5 is just an approximation and not an idealized concept. That takes me to what I believe to be a good candidate for the definition for the square root of 5. Actually, the definition for every square root. Beyond Fibonacci. So this has a lot to do with continued fractions and the quadratic formula. And I won't go into that in too much detail right now. Needless to say, every quadratic function is characterized by a number sequence, just like the Fibonacci sequence. The sequence is modulated by the coefficients of this equation. This sequence approximates a real root of the function. Here's the general Fibonacci sequence. Okay, so it's not the general Fibonacci sequence, but it's the principle of the Fibonacci sequence generalized, where A, B, and C are the coefficients of a quadratic function. It just so happens that the quadratic function for the Fibonacci sequence is x squared minus x minus 1. B and C are 1. Let's look at an example of this. X squared minus 3x minus 1. Starting with 0 and 1, the next term is 3. Continuing, the next term is 10. After almost 30 iterations, we arrive at the following ratio, which just so happens to be a real root of the function. That's all there is to it. Let's design an algorithm that uses this principle to generate the value of square roots as integer ratios to the desired degree of precision. Given root r to approximate, Find a quadratic function where b squared minus 4ac equals r. Use the coefficients of that equation as the modulation for a Fibonacci-like sequence. Follow the sequence to the desired precision. Take the last two elements as a ratio and subtract 1. See the quadratic formula for a description about why this last step is necessary. Let's head over to math.d8data.io under the Rational Compute menu. Roots as integer ratios. I've implemented the algorithm from the previous slide in this app. We start by selecting a seed polynomial. We use the coefficients of this polynomial to generate an additive sequence modulated by those coefficients. This provides us with an integer ratio that approximates a square root. We extract this root from the quadratic formula, and voila, we have our approximation. We adjust the root here, and the precision here. We can increase the precision until JavaScript starts interpreting our integer ratios as decimal values.